Hello, hello, hello. Let us get started on our last sort of condition for partial fraction expansion. So the method that we've been teaching works very efficiently, but there's a couple of modifications that we need to make if it's not the standard basic one. And so we went through the first case, we'll call it, we'll define them. Case one is just a standard approach. That's what we've been doing. Case two is the modification where we have complex roots, which is really, we just treat it the same way, right? The only modification we need to do is just make sure that you're evaluating at the positive complex root. Last case, and all other cases are the same, are or is when the roots repeat. So if you have repeating roots, you have to go ahead and employ a slightly different method. So what we're going to do is we're going to try to see if we can solve the 2s plus 3 over s plus 2, that quantity cubed. And we're going to see if there's anything that we can do to be able to find f of t. So the first thing we're going to do is check. Do we have a table or an image that will match or kind of match what that looks like? So let's take a peek. Grab this one. This one looks like the most basic one. And if you look down here, you have this n factorial over, so let me see if I can click on it here. See if I can get it to zoom in a little bit. I want to zoom. Here we go. So if we look over here, if we have n factorial over s minus a to the n plus 1, does that kind of look like we can perhaps use that over here? Who says yes? Let me go ahead and do a screenshot so you can see. The one that I'm specifically looking at is this one right here. I guess I can't bring it. That one right there, number H or letter H. Go back. Can I use H here?
I don't think so.
Do you all remember what n factorial is? So n factorial, let's say we have 3 factorial. That's equal to 3 times 2 times 1. That's what the factorial means. Do we have n factorial there? We don't, right? Why not? Darn it, we have an s variable in there. So there's nothing we can do. I mean, we could certainly do this, right? Right? That could go ahead and get us to having an n factorial over there. The problem is we still have this expression in there that's not going to allow us to go ahead and go to the table. Anytime you have an n plus 1 power, like if it's raised to more the square power, you can't have an s term in the numerator. So this is a case where we actually have to do partial fraction expansion, even though it looks like we should be able to get something to the table. All right, so let's go ahead and do our approach as normal. So I'm going to multiply. Well, first thing I can do is I got to write out all the coefficients, a plus b plus c, and I have to write them all the way down so that I don't have s plus 2 raised to any power. So I have s plus 2 quantity cubed plus s plus 2 squared plus s plus 2 that raised to the power of 1. Okay? That is going to be over I'm going to have the 3 coefficients, a, b, and c, and I'm going to solve for a just like I have before. All right? So I multiply both sides by whatever is under a. And what ends up happening is cancels, 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 Over here, this becomes a 1, and that becomes gone, right? That cancels out, so you have s plus 2 to the 1. And over here, this cancels out and becomes 1, and that becomes 2, right? So now, if I rewrite it, I have 2s plus 3. Let me go ahead and put it over here, so you have it all on one line. That equals 2 times s plus 3. If I evaluate that at s equals minus 2, well, let's see. That term goes to 0. That term goes to 0. And what I'm left with is A is equal to 2s plus 3 evaluated at s equals minus 2. All right, everybody see that? Everybody see that? That makes sense? We've been doing this all along, right? So that should be something you're getting pretty comfortable with to do partial fraction expansion. This one should be easy. Let's go ahead now and solve for B. Remember, B is over the s plus 2 squared term, right? So if I multiply by s plus 2 squared, here's what I get. That term goes away. That becomes a 1. That becomes s plus 2. Same thing over here. That becomes 1. These will cancel each other out. And then this becomes an s plus 2 squared term, right? So what we end up with is 2s plus 3 all over s plus 2, correct? We just multiplied by whatever's under the b term. Does everybody see how I got there from here? It's just doing the same thing over and over and over again. Okay, so the next step is to do what? Let's see if we got our thinking caps on. What do we need to do to solve for b if we used our standard form?
Should we clear the fraction?
Clear the fraction. How do we clear the fraction?
Multiply everything by s plus 2?
I could certainly multiply by s plus 2, but couldn't I have done that at the beginning if I just multiplied that by s plus 2 cubed?
True.
So I don't want to do any modification to my approach unless I absolutely have to. Why not just go ahead and evaluate at the root, right? Which we've been doing all along. So we're going to evaluate at s equals minus 2. What happens when I say 2s plus 3 over s plus 2 evaluated at s equals minus 2?
Like, you get division by 0 in that first term, so that's not good.
That goes to infinity, doesn't it?
Mm-hmm.
And when I evaluate this term at s equals minus 2, that goes to infinity, doesn't it? So I have a bunch of infinity terms. This term does, in fact, go to 0, but what I end up with is infinity equals infinity plus b. Is that a real number?
No.
It isn't. So that ain't going to work, right? Our approach, that our standard approach, doesn't work. So we're going to modify it. And we're going to multiply by whatever the highest order s plus 2 that we have. In this case, it's s plus 2 cubed. So we're going to end up exactly the same as we did when we solved for A. Everybody see that that's exactly the same as we did for A? Now, what is one way to take this equation and completely get rid of the A term? What's one mathematical expression that you can do? I can't multiply both sides by 0 because that wipes everything out. Is there something else that I can do?
Divide everything by a?
Divide everything by A doesn't make A go away. That makes it a 1, right?
Right.
I need to make sure A goes away. What if I take the derivative of something that is a constant? What is the derivative of this equal to? 0, right? So if I take the derivative of A plus B times S plus 2 plus C times S plus 2 squared with respect to 0, S, what I end up with is 0, by a term, right? Because it's a constant, plus b, because it's b times s, which is just b when you take the derivative of that, plus 2 times c times s plus 2, correct? Everybody understand how I'm doing the derivative? Now, when I evaluate this at s equals minus 2, this term goes to 0, doesn't it? What am I left with? Just left with b, aren't I? So the modification is if you have repeating roots, you've got to take a derivative. So multiply by the highest order coefficient, whatever it is. In this case, it's s plus 2 cubed. Then take the derivative and then evaluate at s equals minus 2. So that's what I've done over here. I've got the derivative of 2s plus 3 equals the derivative of a plus b times s plus 2 plus c times s plus 2 squared. That's going to be equal to the derivative of here. So the derivative of 2 is equal to 0. I'm sorry, derivative of 2s is equal to 2 plus 0. Goodbye, that coefficient. The derivative of a is equal to 0 plus b times 1 plus 0 plus 2c times 1 plus 0 times s plus 2, right? When we do the chain rule. And what we end up with is 2 is equal to b plus 2c times s plus 2. Now I evaluate that at s equals minus 2, and b is equal to 2. Make sense? Let's go ahead and do it one more time and try to solve for our c term, right? But before you do that, you know that if I'm only trying to solve for my b coefficient, I don't actually have to take the derivative of this term over here, do I? Because I know that it's going to be multiplied by at least s plus 2. So if you want to be more efficient, actually just write it as this, because you know that term's going to drop out. So if you just do it that way, then you have 2 equals 0 plus 0, 2 equals 0, sorry, 2 plus 0. 2 plus 0 equals 0 plus b. And then that term is going to go to 0, so you don't even have to do the derivative. So that gets it to you very, very quickly. So what I'm suggesting is, if you have like a third order root, you don't actually have to take the derivative of that term. Makes it easy. So now to go ahead and solve for c, we just take the another derivative again. So we're going to take the derivative of 2 equals b plus 2c times s plus 2. And what we end up with is 0 equals 0 plus 2c. C is equal to 0. Right? If this wasn't going to be equal to 0, then you would just go ahead and evaluate at s equals minus 2.
Question.
Yes.
Since you know the coefficient of a and the coefficient of b, is it even necessary to take the derivative of c? Couldn't you just plug those in and solve for c?
Yeah, so Arthur has a very good point, right? So once I get to this point right here, where I have this expression right here, if I know what a and b is, I can certainly plug in for c, can't I? I mean, I can certainly plug those in and solve for c. So that is a method, but what is maybe the issue that I might have with that? It's a modification, right? You have to remember, like, okay, to solve for this one coefficient, I have to do a different approach to getting that term. So if you want to do it this way, you know, and plug in that value and plug in those two values to get c, that's perfectly fine. I just like doing the derivative one because it's the same approach over and over and over again to get my results. All right, does that answer your question, Arthur?
It does. And actually, can we do the derivative trick to find the coefficient of a?
Yeah, you don't need to.
Okay.
Because
Well,
right
well,
here,
yeah, I mean, I saw that. I just didn't know if there was other scenarios where you might need to do that.
nope, it only is for the, when you expand out or you write out your partial fraction expansion term, when you go to the lesser powers, you only have to do that for those coefficients. For A, it's just a standard approach. There's no derivatives necessary because you see, you actually need the S plus 2 multipliers so that they'll cancel out when you evaluate at the root. Okay. So what we end up with is 2s plus 3 all over s plus 2 cubed equals -1 over s plus 2 cubed plus my b term, I think, was equal to 2. B is equal to 2. Plus 0 over s plus 2. Now we got to make it look like the table. So we're going to go back to our table and see what h needs to be. H needs to be n factorial over n plus 1. So in this case, we see that n is equal to 2, right? Because n plus 1 is 3. So we're going to set that up so that it's in standard form. So n factorial is 2 times 1. So that's 2 over s plus 2, that quantity cube, plus over here, n is equal to 1. So that should be 1 over s plus 2 squared. And I don't have a term over the s plus 2, so I don't have to do that. Now, does 2 and -1, are they the same? It's a trick question. Not even close, right? So all I need to do is factor out the -1. Let me move my equal sign over a little bit.
So you need a leading coefficient of -1/2.
Yeah, because remember, I multiplied the expression by 2, which means I had better divide by that same coefficient, 2. So I have -1/2 times 2 over s plus 2 cubed. Over here, I need a 1, but in fact, I have a 2 over here. So I'll just do 2 over 1. I actually have a 2 multiplier, but I included the 1 there just so that you can see that they cancel each other out, which makes it pretty easy. So my f of t is going to be equal to, going to go back to the table, and I can see that t to the n, e to the minus, or e to the alpha t, over here is going to be equal to t squared, e to the minus 2t. That's -1/2, I should say, up front, plus 2t e to the minus 2t. That's how you will do partial fraction expansion when you have repeating roots. Questions on that? Because that's the last and only case that we have. Yep, great question. So if I'm looking here at my table, right, and I'm going to just go ahead and copy this into whiteboard or whiteboard. Here is what it has to look like. Where's my whiteboard? Okay, that's what it needs to look like. And so if you remember, the first number they had was s plus 3 squared times -1, right? That was the first f of s term that we had. Oh, not square, it's opposite, right? It's s plus 2 cubed. Okay, so now we're going to go ahead and make this look like it, at least on the denominator. This is s minus a -2. So now we see that that looks like alpha. We can, hopefully you can see that alpha, or a, is equal to -2, correct? Now, we know that this is a 3, so that means n has got to be equal to +2, right? You can see that that the actual power it's raised to is the power of 3, and 2 plus 1 equals 3. So n has to equal 3. Which means I need n factorial here in the numerator. n factorial, 2 times 1 or 2, needs to be up here, right? That's n factorial. So you can either write it as n factorial if you want, or you can actually write it as 2 times 1, or you can just write it as 2. It's the same thing. I actually have a negative 1 for the multiplier. So I'm going to move that negative 1. I'm going to factor it out of there. But I put a 2 up here, which means I multiplied the denominator by 2. Because when I factor out a negative 1, I have a 1 left over. Now that I have a 2, I've multiplied it by 2. So to make things correct or consistent, I had darn well better divide by that same term or that same coefficient. So where did I get the negative 1/2? It's because I need a 2 only in the numerator. I have a negative 1, so I have to do a little bit of algebra to make sure I have just the 2 in the numerator. And then this is just multiplication by a constant. Remember how we said multiplication in the time domain by a constant is the same thing as multiplying by that same constant in the Laplace domain? That's why we did that. And we did the same thing when we did this one, right? I had a 2, I need a 1 factorial up there because n's equal to 1. So I have 1 factorial, which means I need a 1 only in the numerator, but I have a 2. So I factor out the 2. And then I have 1 over 1 just to kind of make it consistent. And then I end up with those two ready to go to the table and bring them back into the Laplace, into the time domain. Okay. Questions on that? These are all the cases you'll have to do. These 3. So what Arthur suggested is kind of what I have here. If you don't want to do the case, like where you're just taking the derivative, once you find the a coefficient, like right over here. So we found a. We said a is equal to -1, right? Where's -1? Right over here. So that is our expression. And now what we can do is we can just plug in a equals -1 over here, right? And we can rinse and repeat and do this same process over again. So at that point, you would multiply by the s plus 2 squared, right? And then go ahead and do it that way. But again, I think there's too many constraints there. You're going to set yourself up and make it more difficult. So my suggestion is just do the classical approach. Okay.
I kind of like the derivative trick. That's pretty slick. Not gonna lie.
I think it's great too. It's one of the only times that when you're in the Laplace domain, you're actually going to do derivatives. One of the only times. And they tend to be pretty simple derivatives. You may have to do the quotient rule a couple times, but again, you can ignore the denominator because all that stuff gets canceled away. All right. I was prepared this morning. It's practice time, party time, right? You all get to do item number 1. 5 minutes. Here, I'll zoom way in so you don't get bogged down with the other ones. Please do partial fraction expansion to find what f of t is given an f of s equals 2s plus 3 over s squared plus 3s plus 2. Couple more minutes. All right, what you got? Anybody get the answer?
Almost.
Okay. These are problems that hopefully you should be able to do in just a couple minutes once you get done or once you get familiar with the process. So let's go ahead and spell it out. This is number one. 2s plus 3 over s squared plus 3s plus 2. Very first thing I do, is there anything in the table that looks like this? Nothing close. Nothing works. So I've got to go ahead and start figuring out what the roots are. So I'm going to do the quadratic equation, even though this is a pretty one to factor, but I'm going to do it just because I want to make sure you see the process all the way through. Negative b plus or minus the square root of b squared minus 4ac all over 2a, right? Negative 3 plus or minus square root of 1 over 2, which is equal to negative 3 plus or minus 1 over 2, which is equal to negative 4 or negative 2. Both of those are over 2, which means we have negative 2 and negative 1. So rewriting those in factored form, s plus 2 times s plus 1. Remember, it's the negative of the root is the term that goes inside your expressions. So now we do a over s plus 2 plus b over s plus 1, because we already know that there's nothing in the table that looks like that. We're going to solve for a using our approach. A is going to be equal to, the denominator just shows up there. And then I'm going to multiply both sides by whatever the coefficient I'm trying to solve for. In this case, it's s plus 2. So the s plus 1 is left because s plus 2 cancel. And then I evaluate at the root. That becomes 2 times minus 2 plus 3 over negative 2 plus 1, which is equal to negative 4 plus 3, which is negative 1 over, whoops, negative 1, which means a is equal to 1. Same exact thing for B. B is going to be the numerator, and then I'm going to cancel out whatever expression is multiplying in the denominator. In this case, it's s plus 1, so goodbye s plus 1. Evaluated at s equals -1. So that becomes 2 times -1 plus 3 over, s plus 2, not s plus 1, over -1 plus 2. That means I've got 3 minus 2, 1 over 1 is equal to 1. So my f of s is going to be equal to 1 over s plus 2 plus 1 over s plus 1. Now I can go back into the time domain. That's e to the -2t plus e to the -1t, or e to the -t. Questions on how to do that?
Put your factor numbers in.
You did what?
I did s plus 1 and plus 2 to my a with the numerator over s plus 1 when 0 equals 2. How do you know which one to put where?
Well, I'm not quite understanding your question, but remember, to solve for a, I'm going to multiply both sides by what the a is over. So I can see it's s plus 2, which means the s plus 2 in the denominator here is going to cancel. So all I have left is s plus 1.
That quadratic equation, when you get your -2 and your -1.
-2 and minus, okay, yeah, right here.
Yeah. Put it into your denominator of the function.
Right over here.
If you know whether which one is going to be for the
Doesn't matter.
doesn't matter.
Does not matter. You can, as long as you do the calculations correctly, you're going to end up with the right coefficients in the numerator. So it doesn't matter.
Right.
Feel good about that? All right, let's do the second problem. Let's do number 2. Give you 5 minutes. I can't. It would probably make it not legible. I mean, I could try to put it in this document here. Let's see how illegible it'll be. And I'll just highlight the ones that you'll really need. I'll just go up to here. Is that okay? Is that better? Couple more minutes. All right. Anybody get number 2? Is that a yes? Are these too hard? Do you want more time, or do you want to show the approach? Okay. Do 2 more minutes. But we got to be able to do these a lot quicker, right? Because remember, during an exam, you may not have 10 minutes to do a problem. These, hopefully, once you get efficient, under a minute, be able to crank these out. Maybe 30 seconds. Because the homework will be due a week from today, right? That's a sign for this. We already gave you one problem. Okay. That was a couple minutes. So I just, while you guys were working, hopefully you already did the quadratic equation, so I don't need to explain it. But what you ended up with roots, -2 plus or minus j. Hopefully everybody has gotten to the point where they know the roots. So now all we're going to do is rewrite that as 2s plus 5 over, and we're going to put it in standard form. Remember, it's s minus the real root squared plus, not the j term, but what multiplies the j term squared. In this case, that's 1, right? It's just 1j, so that becomes 1 squared. So just making that look a little nicer, s plus 2 squared plus 1 squared. Well, let's see if there's anything in the table that kind of looks like that. I see one. Do you see one? I see letter K. Sorry, not letter K, letter I, right? Drew was right. He said I, but I said K. No, it's I. I is the correct term. So all we need to do is make it look like I. So I has a B, which is the imaginary part. It has to look like B over S minus A. Come on. S minus A squared plus B squared to be able to use that one. So this, we notice, has an S in the numerator. Uh-oh, we don't have that here. We have a B term. Well, let's break this term out. 2S over S plus 2 squared plus 1 squared plus 5 over S plus 2 squared plus 1 squared. And if you go back, there's another one. So this is the sign. This is E to the minus alpha t, or AT, sine of BT. S over S minus A squared plus B squared is equal to E to the minus AT cosine of BT. Boy, oh boy, I have an S up there. So all I need to do, move the 2 out front, that becomes S over S plus 2 squared plus 1 squared. Check, I got the cosine one done. Over here, I need B, which means I need a 1 over there. S plus 2 squared plus 1 squared, right? So now my f of t is 2 e to the minus 2t sine of omega t. Omega is equal to 1, so that's t, plus 5 e to the minus 2t cosine of t. I didn't even need to do partial fraction expansion where I had to solve for coefficients. I just needed to break those up into the 2 terms. Question on item 2. From here to here? So if I have complex roots, it's always S minus the real part plus the imaginary part squared. That's just the formula you use.
So what if you, because in my case, I didn't use the quadratic equation as exactly about.
But you had complex roots. You're good enough at math to figure out that these were complex roots?
Well, no. I mean, like when I factored, the denominator,
Yep, the S squared plus 4S plus 5. What did you end up with factors?
x plus 5 and x plus 1.
Let's check Homa's work. She said S squared plus 4S plus 5 equals S plus 1 times S plus 5. Is that correct? Is that what you said?
No, that's what I said, that's not right. So I'm not gonna-
What do you end up with? Is that the same as that? That's why I don't factor. Quadratic equation, right? I know nobody wants to, but on both of these problems, even the first one was pretty easy. I still did the quadratic equation to make sure it's like I know what the answers are. Because this one, it does trick you, right? Oh, it's S plus 1 times S plus 5. Or S plus 1 times S plus 4, which would have been probably the one if I would have done if I tried to make them real, but it isn't a real number. That's why you do a quadratic equation. All right, let's do number 3. 5 minutes. You don't even have to do quadratic equation in this. That's so magnanimous for you. Let's see if you can get this done in 5 minutes. Yep. Couple more minutes. Think of that. I thought those were little vanilla wafers.
No, yeah.
As I say, I can be a world class athlete with eating vanilla wafers, but prove me wrong. Although probably still not the best breakfast, right?
No, but it was Minecraft.
Not a lot of protein in those things.
Get it. Really fun.
No, but aren't you as an athlete, you're supposed to have like a certain amount of protein with every meal?
I do.
Did you succeed this morning?
No, not smart at all.
They don't have hard boiled eggs over there or smoothies?
No. They have smoothies, but they didn't make them this morning. So,
The hell with the protein.
think about
Let's say that's the number one thing for most athletes is nutrition. All right, how'd you make out? It was 5 minutes. Get the answer? Get close?
that one didn't-
That one didn't go so well?
No.
Let's do it then. Number 3. I have 5 over s squared. Times s plus 1. And I can see right off, there's nothing in the table that nowhere looks anywhere near that. So I'm going to go ahead and do my partial fraction expansion. Remember, when I have repeating roots, I have to take it all the way down to the s to the 1 coefficient plus c over s plus 1, right? You can solve for any one you want. We'll just solve in order. A is going to be equal to 5 over s plus 1, evaluated at s equals 0, right? Because that's the root. That's an easy one. That's 5, right? B is going to be equal to 5 over s plus 1. I've got to take the derivative of that with respect to s and then solve for s equals 0 to get this coefficient to drag out. So what is the derivative here? You got to do the chain rule, or no, the quotient rule. So it's the derivative of the numerator times the denominator minus the derivative of the denominator times the numerator all over the denominator squared. Y'all remember that from Calc 1? And then I evaluate that at s equals 0. So what I end up with is negative 5 over s plus 1 squared, which means b is going to be equal to negative 5. Right? So that one was a little more work for the derivative. And then lastly, c is going to be equal to 5 over s squared, evaluated at s equals minus 1, which means that is 5. So my f of s is going to be 5 over s squared minus 5 over s plus 5 over s plus 1. So my f of t, just looking at the table, is 5. This n's equal to 1 here, right? N's equal to 1 because that's 1 plus 1. So that's 1. That's 1 over s squared. So that's just, well, let me write it out because it'll look a little confusing. That's 5 times 1 over s to the 1 plus 1 minus 5 over s plus 5 over s plus 1. So that's 5t, either n minus anything because it's 0. So that's 5t minus 5 plus 5 e to the minus t. That's number 3. Last one, number 4. Go ahead and give it a whirl. 5 minutes. This one we will need to do quadratic equation. How about I do that for you? So that way you don't actually have any issues. So you have 100 over S, 100 times S plus 1 times, and I'll just do the quadratic equation over here. -4 plus or minus 16 minus 4 times 12. No, 4, that's 40, 52. So 16, so that's the square root of -36 all over 2, which is -4 plus or minus 6j over 2, -2 plus or minus 3j. So that becomes S plus 2 quantity squared plus 3 squared. Now do partial fraction expansion for that. We know nothing looks anything remotely like that in the table, so you get to do this one. More minutes? All right, what'd you get? Did you get him? Not sure how to do it or not had enough time? Time? Well, why don't you all keep working? And I'll just put it up so that if you rewatch the video, you can follow along. I know human nature is going to peak, but that's okay. So this is A over S plus B over S plus 1 plus, oh boy, complex number, S plus 2 squared plus 3 squared. So A is going to be equal to 100 over S plus 1 times S plus S squared plus 4S plus 13. And the only reason why I substituted in the original polynomial is just because it's like, I don't have to plug in 0 and do all that stuff. I can just see it's going to end up being 13. Evaluate that at S equals 0, 100 over 1 times 13. Not too bad. B is going to be equal to 100 over S times S squared plus 4S plus 13. Evaluated at S equals -1. -1 times -1 squared is 1. -4 plus 13. So let's see, that means I have 100 divided by -10. I did that one right. 1 plus -4 is 3, or -3, plus positive 13 is 10, and then I have a negative there, so I have -10. The last one I need to do is C at an angle of theta, which is 100 over S times S plus 1, evaluated at S equals -2 plus 3J. This one is not easy to calculate. -2 plus 3J times -1 plus 3J. And that equals, so I'm gonna bring up MATLAB to do that one because I can't do that one in my head. So I have 100 divided by, I'll put 2 parentheses, -2 plus 3 times J times -1 plus 3 times J. That's my answer. So I'm going to go ahead and let's just make that a variable. I'll call it EET. And then I need to display the magnitude. Oops. 8.77. And then the angle, multiply that by 180 over pi because I'm going to display it in degrees. 127.9. So now I have my f of s equation. So this is going to be equal to 100 over 13, or minus 10, or this is over s, minus 10 divided by s plus 1, plus c at an angle of theta goes out front here, because I need to have a 3 over here to make it look like the table. So by multiplied by 3, I had darn well better divide by 3. So my f of t is equal to 100 divided by 13 minus t e to the minus t plus 8.77 divided by 3 e to the minus 2t sine of 3t minus 127.9 degrees. Anybody get that answer? Anybody get close? Because for this semester, being able to go back and forth in the time domain is really important. So you have to be really good at doing partial fraction expansion to go back into the time domain. But that finishes up introduction to Laplace, and then introduces our next topic. Exam 2. Friday,
Which letter?
week from Friday.
Oh,
Okay, yeah.
I've asked Mark to do more partial fraction expansion practice during lab this week, so not doing like an actual circuits lab, but doing a lab where you're gonna be just doing some partial fraction expansion. And then have your test a week from today, a week from Friday. Make sense? The other class I teach, they also have the exam on that Monday, just happens to work out that way, but because there's enough of a space, right? There's 4 days versus if they did Monday, Friday, you know what I mean? It wouldn't be a huge advantage. So rather than wait a week, we'll just put them in the same week because there's enough of a gap there. Any questions on Laplace? Because we're going to be actually starting to solve real world systems in differential equations, but not really, because we're going to take them to Laplace domain. So we're going to write differential equations using our circuit analysis techniques that we've been studying at the beginning of the semester. And then we're going to actually come up with the time domain results using Laplace. So this is where the EETs, right? Most likely you haven't had calculus-based circuit analysis. Now everything is calculus-based, but we don't actually have to do a lot of calculus because we can take advantage of Laplace. And so your understanding of circuit analysis and getting consistent results should be really good, especially as the world moves to faster and faster processing. We now have to start looking at transient and how things decay over time, not necessarily just steady state. All right, TV land, any questions? Because that's all I had for today.
No, just you gotta practice it is all. It takes a while.
Yes, but once you get used to the process, I'm telling you, you'll get so competent at these things, it will take you just, seconds to do a problem. And one of the things to note too, this is a big thing on the FE, is being able to do stuff with Laplace. So being able to do circuit analysis, what we'll be doing in the next sort of module is pretty important. Nothing else, party people?
No, thank you though.
All right, y'all. Have a wonderful day. And I will see you all on Thursday. Take care, everyone.
Thank you,
Have a good
Paul.
one, Paul.
Thank you.